Mr. Rainsberg here to finish you up with lesson 11.2, where we dive into a new chi-squared statistic, chi-squared test for association or independence. But first, we're going to do something called a follow-up analysis, where we look at what contributes the most to our chi-squared statistic and what does that allow us to conclude. So we're going to be addressing the blue objectives that you see over here in this video. So let's just jump right into the follow-up analysis. So we looked at a chi-squared test for homogeneity. And that allowed us to take a categorical variable and look at the distribution of it across different populations or treatments. And when we did that, we went through the whole state, plan, do, conclude, four-step process. And when you conclude, if you reject the null and you conclude the alternative, then that means what you saw was so far away from what we expected to see, it probably didn't occur by chance. And we can do a follow-up analysis. And we can look at what contributed the most to that chi-square statistic. Which individual components had the most impact on that value? And when you do that, you have to keep something in mind. You have to also remember it's not just about which has the greatest impact, but it's also about how, in what way. What we observed, was it way higher than what we expected, or was it less than what we expected? So we actually have to dive deeper into that number, because remember, when we're doing our components and we're looking at what contributes, those are going to be positive. But we have to go into the observations and look at what we were expecting to see. Is it what we observed less than or greater than what was expected? So don't just say this number had the highest impact when it comes to the chi-square statistic. You have to address how does it have the highest impact. Is it because we observed something way higher than what was expected, or do we observe something that was way lower than what was expected? And we're going to look at this when it comes to our wine problem, which was the first example that we dealt with in the previous video. So let's go back and look at the results for that one. So if we look over here, this is our problem that dealt with the wine being purchased based off the music being played. And we came up with a chi-squared statistic of 18.28, and we even looked at the observed and the expected. We're going to dive deeper into this observed and this expected, along with this contribution. What had the highest impact on the chi-square statistic and why. So this is from the slides that we did already, and what I have next is a mini tab output that breaks it down further. And I have it labeled for you, and I would write this down that the 1, the 2, and the 3, those are the types of wines that were purchased. So 1 is the French wine, 2 is the Italian wine, and 3 is the other wine. And the top headers, the non, the French, and the Italian, that's the type of music that was playing in the store when the wine was purchased. And we can see there are these two highlighted parts here. This 1, this 9.57, this 7.672, and this 19, 10.72, 6.404. Now those two areas had the biggest impact on that 18.279 that we see in the bottom. Also notice in the bottom it has the p-value and the degrees of freedom. That's nice of Minitab to do that for us. Now, those two had the biggest impact, and we're going to keep that in mind. Now, 7.672 had the largest impact. And we don't just say it had the largest impact or was the biggest contributor. We could take that 7.672, divide by 18.279, and write it as a percent. It makes up blank percent of the chi-squared statistic. So what we can also say is our observation of Italian wine sold when French music was playing, because that's that intersection, French music and Italian wine, is lower than what was expected. And so if you look at what we observed 1, but we expected 9 if it was the same across all the different treatments. So, well, it's extremely low. So that means the largest contribution of the chi-square statistic came from that. And it made up 42% of the value. But we have to keep in mind that we have to state the direction. It was lower than what we expected. And if you look at the other one, you have the Italian music with the Italian wine, and you see we observed 19, we expected 10.72. So in this case, our observation of Italian wine when Italian music was playing is higher than what we expected. So notice I'm using descriptive words here. I'm saying it's higher. We observed more than what we expected, or we observed less in the other case than what we expected. It's the second largest contributor of the chi-squared statistic. It makes up 35% of its value. So these two areas contribute the most to that chi-squared statistic. And that's kind of what the follow-up analysis allows us to do, to go deeper into the components and figure out which ones had the greatest impact and why. Is what we observed larger than what we expected, or is what we observed smaller than what we expected? And that's what you need to go through and describe when you're doing a follow-up analysis. Some things to be careful with is many studies do involve comparing the proportion of successes for each of several populations or treatments. And in Chapter 10, we looked at two sample z-tests that allowed us to test the null hypothesis that, population proportion 1 equals population proportion 2, where those are the actual proportions of successes for the two populations or treatments. Now, a chi-square test for homogeneity allows us to do it for more than 2. We can do it for P1 equals P2 equals P3 equals P4, ... piece of K. Now, we could write it all out that way algebraically, or we can state it, hey, the null hypothesis says that there is no difference in the proportions of successes for the K populations or treatments, insert context there. The alternative says, hey, at least 2 of them are different, because one of them is different, it's going to at least impact one other one. So we need to be careful. Do not state the alternative hypothesis as all the proportions are different, because some of them can be the same. We looked at the follow-up analysis. We saw that some of them were very close to what we expected. Others were further away. So when we're thinking about the alternative hypothesis, it's not all proportions are different. You need to think about it in the way that, the opposite of that all the proportions are equal is that some of the proportions are not equal. And so that's something to keep in mind with the alternative hypothesis, is that there is no difference and that there is a difference. And what that is a difference means is, at least 2 of them aren't going to be equal. Some of the proportions are not going to be equal. So we're going to look at another chi-square test for homogeneity, and this one looks at the prompt, cocaine addicts need cocaine to feel any pleasure. So perhaps give them an antidepressant drug will help. A 3-year study looked at 72 chronic cocaine users and compared an antidepressant drug called desipramine with lithium, a standard drug to treat cocaine addiction, and a placebo. 1/3 of the subjects were randomly assigned to receive each treatment. Here are the results. Now, I wrote in some of the totals for us there to make it a little bit easier, but I'm also going to do something else. I'm going to highlight, there's 72 chronic cocaine users that were in this study, and I'm doing that because notice 48 plus 24 is 72. The total there is 72. I'm going to need that number. And then I'm also going to highlight this randomly assigned. Now, the reason why is this: if I read the whole prompt carefully, I will see that this is really an experiment. And that means when we are doing the plan process and we're looking at independence, we do not use the 10% condition because this is an experiment in itself. So that's something to keep in mind when I'm reading. So we have our information, and we're going to look at the state. Now, the state, we can phrase it this way. We can say what we're used to. There is no difference in the relapse rate for the 3 treatments. So we're looking at the relapse rate here. And the alternative says there is a difference in the relapse rate for the 3 treatments. So this box right here shows you the way we have written it in the past. Now, we can still write it this way. I want to show you another way you could do it, and this is more algebraically for the null hypothesis. It could say the 3 proportions for the populations are equal to each other. P1 equals P2 equals P3, and that's based off of group 1, group 2, group 3, which we see in the table. And that is where the P sub I is the actual proportion of chronic cocaine users, like the ones in this experiment, who would relapse under treatment. And notice it has the alpha equals 0.01 level. The alternative is at least 2 of these are going to be different. And so we can write it that way, or we can write it in the way over to the other side. So this is kind of going over with that whole thing talked about in the previous slide. We can say that they're all equal to each other, or we can say, hey, at least 2 of them are going to be different. But we got to make sure we define what the proportion is in context. So now we're on the plan step. Now remember, in the plan process, you always want to state what test you're dealing with. We're dealing with a chi-square test for homogeneity. And we need to go through random large samples and independent. We already kind of had a clue about independent when we were reading the prompt. Now the random, they were assigned to different treatment groups. Do not say, we use a simple random sample. No, because this is an experiment. They were assigned randomly to different treatment groups. Now in the large sample, we have to look at the expected counts. And those expected counts come from assuming that the null is true. And we did learn that there was a process we could use for that. When we're assuming the null is true, we can do our row total times our column total, and we can divide by the table total. We had that formula from part A, and we're going to use that here. And I want to show you that's kind of what we can see with the abbreviations off to the side, to the left of the table there, is we're going to take this first one, the deciper mean, and if we look at this with the yes column, and we're looking at that, well, the row total is 24, the column total is 48, and my total, the table total, is 72. And so if I look, I'm going to do 24 times 48 and divide by 72. Now what's interesting, and notice you can see I did a bunch of them already for you, if I go down here, that is also 24. So that would be 24 times 48 divided by 72 as well. And if I continue down to the placebo and yes, cocaine relapse, they have, again, 24 times 48 divided by 72. So these all happen to have the same expected counts there. Now we could do it for they do not relapse under treatment. So now we're looking at the no column. And we're looking at the row totals, the column totals, and I can still go through and show you. So let's just kind of erase this. And if we look, we have, for the no column, we still have 24 as our row total. We have 24 as our column total now, and we're going to divide by 72. And what's interesting is if I go and I'll use a different color this time, and if I go look at the lithium, we have 24 for our row, we have 24 for our column, and we have 72. So that's what I have right here. And if I did it for the placebo as well, we would see the same thing. We would see that we have, for this row, we have 24 as our total, we have 24 as our column total, and 72. So these all happen to be the same thing. Now what's nice is all of these expected counts, they are greater than or equal to 5. So I have my expected counts, all are greater than or equal to 5, so I can continue on with finding the chi-square statistic. Now independence. Remember, we're not dealing with the 10% condition because this is an experiment. Random assignment helped create 3 independent groups. And if this experiment is conducted properly, knowing one subject's relapse status should give us no information about another subject's outcome. So therefore, individual observations are independent. So plan step is always where the big stuff is, a lot of the writing is. Remember, you name the test, you look at random, you have to look at your expected counts, assuming the null is true. Row total times column total divided by total, and you're going to have the same amount as the cells themselves. So here we had 6 cells in the table, and I have 6 of them. There just happen to be a few of them that are the same. You have to make the statement that it's greater than or equal to 5, and then you have to address independence, which in this case was an experiment. So we had to make sure a random assignment created 3 independent groups, and that knowing one's outcome is not going to affect the other ones, so that individual observations are independent. So now, the do step. The do step means get your calculator out, and we're going to look at calculating the chi-square statistic. Now, for showing work, there's not much we need to show. We want to do observed minus expected squared, divide by expected, add them all up for the number of cells in the table. But what I would do is I would write down the first 2. So we observed 10, we expected 16, subtract that square, divide by what we expected, 16. Plus, do the next one, 14 minus 8, square it, divide by 8. So look at the table as we're doing this from the previous slide. And I'm just going to go right down to the last cell, 4 minus 8 squared over 8. I'm going to show the first 2 being added, the dot, 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 and the last one. And then I'm going to go right to my calculator. And by going to my calculator, I'm going to keep in mind where I need to go. And in this case, it was shown to you in the Part A video, you want to go to your matrix. So in my matrix, which is that second x to the negative first power, I am going to type in the original table. So let's pull up the calculator and follow these steps. So here we are with the calculator. I'm going to hit second x to the negative first, and I'm going to go to edit. Now, our table is going to be inputted into matrix A. And so I'm going to go there, and it was a 3 by 2 table. 3 rows, 2 columns. So I input 3, and I do 2, and then I type in all the information. And that is the information that's on your slides, 10, 14, 18, 6, 20, and 4. Make sure you hit enter after every time to input them into matrix A. Then once those are done, hit second mode to quit. And you want to go to stats, test, and we're going to use a chi-squared test. Not a goodness of fit. Go one higher, go to the chi-squared test. I'm going to hit enter. The observed should automatically have A there, and the expected should automatically have B there. And we don't want to change those. So I'm going to hit down, down. I'm going to go down to calculate. Remember, you could also choose draw. Now, the reason why I want to look at calculate is because that gives me my chi-square statistic of 10.5. It gives me a p-value 0.0052 approximately, and it even tells me my degrees of freedom. That is so nice of you. And now let's write these down. And so we're going to write these down, put them on your notes. So you can see I wrote down the 10.5 there for our chi-squared. Again, I just showed the first two, the last one, but I'm going to let the calculator do all the work for me. It gives me 10.5. I also give my degrees of freedom. The calculator did tell me it was 2. Remember, it's number of rows minus 1 times number of columns minus 1, which gave me 2. And that gave me a p-value of 0.0052, which is really nice that it did that. Now, remember to sketch a graph. So I could even use that and do a quick sketch of the graph. And if I look at that, notice what I have here. I can see it's a right skewed graph, and I can see it's going to be way over in that tail. Way over in that tail. What does that mean if it's way over in that tail? So I have the graph. Well, our p-value of 0.0052 is less than our alpha level, which means we reject the null and we conclude the alternative, which means we have sufficient evidence to conclude that the true relapse rates for the 3 treatments are not all the same. So a lot of it is the plan step, and then you have to know how to use your calculator when it comes to the other parts, with the chi-square statistic and finding the p-value. So that was a chi-square test for homogeneity, looking at an experiment. Now we're going to look at another relationship between two categorical variables, and it's another common situation, and it leads to another two-way table. It's going to take a single random sample. Notice it says a single random sample. It's chosen from a single population. Then it's classified to two categorical variables. So that's a little bit different than what we did for our chi-square test for homogeneity. We have a single random sample of individuals chosen from a single population, and then we're looking at the distribution of it across different categorical variables, two categorical variables. Here we have another prompt to read, and it says a study followed a random sample. I highlighted that. That tells me I'm doing the 10% condition for the independent step of 8,474 people with normal blood pressure for about 4 years. All the individuals were free of heart disease at the beginning of the study. Each person took the Spielberger Trait Anger Scale test, which measures how prone a person is to sudden anger. Researchers also recorded whether each individual developed coronary heart disease, CHD for short. This includes people who had heart attacks and those who needed medical treatment for heart disease. Here is a two-way table. Now notice what I have written down right here. One sample classified by two categorical variables. And that's something that's really nice to kind of write down, because that's really what's being talked about up here, is you have one sample that's being classified by two categorical variables. Our one sample, we're looking at the CHD and the no CHD. We're looking at a two-way table for that. So this is where we have a new chi-square test. One sample classified by two categorical variables. So we're interested in whether angrier people tend to get heart disease more often. And we can't compare, and notice I have highlighted in gray here the totals for the rows and the columns. We can compare the percents of people who did and did not get heart disease in each of these three categories. And that's what we're doing here in this step. And then down here we have a visual representation of a graph of it to help it, to analyze better. And what do we see? We can see that there is a clear trend. As the anger score increases, so does the percent who suffer heart disease. And you can see that there is a clear trend. You have the low, then you have the moderate, and then you have the high. There is a clear trend that the angrier people are, the more prone they were to get this heart disease. But can we make that as a full conclusion? We don't know yet. But, we can look at it and go, a much higher percent of people in the high anger category develop CHD than in the moderate and the low. So, and a much higher, compare them. Look at the numerical comparisons, 4.27% to the 2.33%. By the way, if I add those together, the 2.33 and the 1.7, the two lower categories, the higher is actually larger than those two combined. So that's what that last one's saying. It is a much higher percent of people in the high anger category who develop CHD than in the moderate and the low anger category. So we think there's something there. So let's dive deeper with another chi-square test. And that is the chi-square test for association and independence. And what this does is it takes a random sample, and if we arrange them in a two-way table to see if two categorical variables are associated with each other. And this one is looking at the anger level and the CHD, the heart disease. Now, keep in mind, what it's really telling us is, hey, you're taking one sample, and you're looking at, is there an association between two categorical variables? Those categorical variables, anger level and heart disease. We're going to turn them into percents to look for a relationship between them. Our null hypothesis and our alternative hypothesis is really following the same general structure as what we're used to. But now we're going to say that there is no association between the two categorical variables for the null hypothesis, and we're going to say that there is an association for the two categorical variables for the alternative hypothesis. So you can see right here here's an example of our null and alternative written in that form. There is no association between anger level and heart disease, the two categorical variables in the population of people with normal blood pressure. Or there is an association between anger level and heart disease, the two categorical variables in the population of people with normal blood pressure. That's one way of saying it. Now, another way of saying it is that if there's no association, that's kind of saying that they're independent of each other. If there is an association, that's kind of like saying they're not independent of each other. So do keep in mind that we looked at this idea of independence and not independent before. But when you're using these, do you see something different about how the null and the alternative are written? We are trying to say the two categories, anger and heart disease, are independent of each other. And insert context. The alternative, anger and heart disease, the two categorical variables we're analyzing are not independent of each other. So this one looks at saying, hey, there's an association between them. This one says there is, is it independent or are they not independent of each other? So these are two ways of writing the same thing. So let's now kind of outline everything for a chi-square test for association or independence. So we have all our information here for the chi-square test for association and independence, and this deals with the conditions, random, large sample, and independent. Notice those are the exact same, which is really nice. So for a chi-square test for association and independent, there are two ways of writing your hypotheses. The first one deals with association. There is no association between the two categorical variables in the population of interest, or there is an association with the two categorical variables in the population of interest. Another way of writing it is by looking at it with independence. The two categorical variables are independent of each other in the population of interest, insert context, or you have the alternative here that says the two categorical variables are not independent of each other. Now, I just kind of remind you what independent meant when we dealt with chapter 5 in probability. The probability of B given A is going to be equal to the probability of B. That the event B, given that event A occurred, the probability of it is not going to change if it just occurred by itself. That's really what you're kind of saying here when it says that the two categorical variables are independent of each other. I'm not going to write it down, but right here it says find the expected counts. We have that formula. Row total times column total divided by table total. That's a way for us to do the expected counts. And we even looked at how to use our calculator to help us out with it. We have our chi-squared statistic, observed minus expected, squared divided by expected, add all those up together. So that's the same. It's the sum over all cells, not including the totals. Now, again, our degrees of freedom is something we need to keep in mind. I have it highlighted down there. It's the number of rows minus 1 times the number of columns minus 1. The p-value is going to be the area to the right. So a lot of this is very similar. I mean, for how you calculate the expected counts, that's similar. The conditions, that's similar. The chi-squared statistic calculations, that's similar. The degrees of freedom, that is similar to homogeneity. And the p-value being the area to the right, wow, that's nice. So some of these are the same. It's the which test am I dealing with, and how do I state my null and state my alternative. So we've already looked at the anger level and the CHD heart disease prompt, and we're going to dive deeper into a full state plan do conclude with that same prompt. So you can always refer back to it. Here is the observed table and the expected table. Now, don't worry, I'll show you how to use your calculator again to find that expected table. But let's just kind of go into the whole inference procedures here. We want to perform a test of, now again, this is taking one sample, and we're looking at a relationship across two categorical variables. Is there an association or is there no association? Are they independent? Are they not independent? And those two categorical variables are anger level and CHD heart disease or no heart disease. So we have those two. Anger level and heart disease are the two categorical variables. So your categorical variables, wow, those are the headers for the rows and the headers for the columns. That's nice. So our null says there is no association. There's no difference. There's no association between anger level and heart disease in the population of people with normal blood pressure. Or our alternative says there is an association between anger level and heart disease in the population of people with normal blood pressure. And we're going to use an alpha level of 0.05. Wow, that's unique. So notice how we wrote our null and alternative. We're doing it based off association here. There is no association or there is an association between the two categorical variables across the population of interest. All that was context from the prompt. So now on the plan, remember this is where a lot of your writing is going to be, so do pay attention. You have to, looks like name the test. This one's a chi-square test for association or independence. And we're looking at random. Now remember, they had a random sample of 8,474 people with normal blood pressure. Large counts, and this is what we're looking at next. Well, for the large counts, they have to be at least greater than or equal to 5. And you can see that I have all the information here when it comes to your calculator. I will pull up the calculator and show you again how we go about doing each of these parts over here. And you get your expected counts. Now, I can say, be sure to write. And even though your calculator does it, do pay attention because I'm going to go to my calculator now. Is write down the expected counts on your paper. You must show them that all of them are at least 5. You can't just say, hey, they're all at least 5. You have to show them all the expected counts. So let's go ahead and look at the calculator. So where do I go again? Well, those pictures showed the matrices. So I'm going to hit second, x to the negative first, and go to matrices. Now I want to go over to edit. And I'm going to edit matrix A. And in this case, it is 2 rows by 3 columns. And I have all the information from the table on your slides already inputted there. And you're just going to type in the original observed. So you type, in matrix A is your observed. The calculator will find all the expected for you. Don't do all that math. And so I type all those in, and hopefully my talking is giving you the time to do that. Then I'm going to hit second quit. I'm going to go to stat, go over to tests, and I'm going to choose not chi-square test of goodness of fit, up one more to chi-square test. So notice chi-square test for homogeneity and chi-square test for association and independence use the same part in our calculator. Interesting. So I have observed as matrix A. It's going to output it in the expected in matrix B, and I'm just going to hit calculate. And we have our information, we have our p-value, but wait a minute. How do I look at my expected counts? Well, it's stored in matrix B for you. So I can hit second matrix, and I can look at, I can go over to edit if I want to, and go down to matrix B, and there are all of my expected counts. So I can see all of my expected counts now. So before we calculated them, then I went to the calculator for you as well. I never showed you how to find them though. To find them, I can go that way, or what I can do is I can hit second, x negative first, and just go down to matrix B here and hit enter, and then hit enter on my screen. Now, I don't like this because they're all decimals, and I have to keep scrolling to the right to see all the information. It's going to give me all the decimals. So that's the other way of seeing it. But I can see all those expected counts, and I can write them down. So hopefully, so if I boom, boom, go over to edit and choose matrix B, hopefully you can write all those down, and I've given you enough time with the talking to do so, or pause the video. So I wrote them all down, and the way I did it was I copied the calculator screen and pasted it over there, because I can. And so what you do next is you look at independence. Knowing the values of both variables for one person in the study gives us no meaningful information about the values of another person. So that means individual observations are independent. Because we're sampling without replacement, we have to check the 10% condition, because this is not an experiment, it's a sample. And I can say that the people with normal blood pressure, it's reasonable to assume it's more than 84,740 people. So now we're at the do step. And what's really nice is I already did that step, didn't I? When I ran the test, I went through and I calculated my statistic, which is really awesome. And so I have my degrees of freedom. I do the first two, ... the last one. I have my calculator sketch a graph for us. And there it is, and I get my chi-squared value. I have my degrees of freedom. Now I can use table C. I can go to the row that is assigned to degrees of freedom of 2. And I could try and find where does 16.077 fall. But my opinion is if we're using the calculator to do the expected values for us, you might as well just finish it with the test and get the values and get it along there. So in that case, I can look across and I can see what's going on. And it's way beyond the 15.20. If you were to look at table C, that 15.20 is that the largest critical value. So we're beyond that. So we're beyond that number there. But I'm going to use my calculator. Now, I did do something different here. I did use calculator and it calculated it right here for me. And I also can use my calculator and look at that chi-squared CDF, which Mr. Manico showed in his video. And so I have my lower bound, 16.077, my upper bound, and 1,000, and then my comma degrees of freedom, which in this case was 2. And that gives us 0.00032, which is the same as that number. So there's a couple ways you can use it. So now we can conclude. Because our p-value is clearly less than our alpha level, we can reject the null. And we can conclude anger level and heart disease are associated with each other in the population of people with normal blood pressure. So we can't conclude that null. We rejected the null that says that there is no association. And when you reject the null, you conclude the alternative that there is an association between your two categorical variables, anger level and heart disease. And that's what our conclusion is stating here. So this lesson looked at two different tests, a chi-square test for homogeneity and a chi-square test for association and independence. And be wise with these. Use the chi-square test wisely because they are very similar to each other. I mean, notice the work that we did with the calculating the test statistic, the degrees of freedom, the way it's presented in a two-way table, even though a calculator steps are the same, finding the p-value is the same. They're so similar to each other. So you read this part right here, and the questions that these two address and answer are different from each other. And we can, a nice way of figuring out is by looking down here, and it says this, instead of focusing on the question being asked, it's easier to look at how the data were produced. If you have two or more independent random samples or treatment groups in an experiment, you do a chi-square test for homogeneity if you're looking at how does it relate to more than one categorical variable. So if we have two or more random samples, so if we're collecting two or more random samples presented and we have a two-way table, we're going to do a chi-square test for homogeneity. If we have a single random sample classified according to only two categorical variables, we do a chi-square test for association and independence. So if we have two or more independent random samples, then we're going to be looking at the chi-square test for homogeneity. If we have one single random sample classified according to the two categorical variables, that's a chi-square test for association and independence. So you have to look at how it's presented to you. How was the data collected? How was it produced? If it was more than one, two, or more independent random samples, there's a very good chance we're going to the chi-square test for homogeneity. If it's one random sample, one single random sample, we're looking at the classification between two categorical variables, and that's association or independence. So hopefully that helps clarify a little bit more the difference between association and independence chi-square tests and homogeneity chi-square tests.